Hey guys, in this video I'm going to show you how to use the secant method to solve a nonlinear equation. Actually, this method is very similar to the false position method that I illustrated and explained in the previous video. There is a slight difference that I'm going to show you later in this video. Let's look at this method. Uh, Similar to the false position method, the function fx should be continuous for the interval that we are looking for. Also, the value of the function at the lower and upper bounds of the interval should not be equal, and also their multiplication should be negative. Here we have the graph of fx in red, and we are looking at the interval of a and b. Let's call a as x subscript minus 1 and b as x0. Okay, we draw the line, the secant line between fa and fb, and this is the line. The intersection of this secant line with x-axis, we call it x1, and we seek the value of fx at this point. So it's going to be this point. Okay. At this new point, we draw the secant line between this point and the previous point. So it's very important to pay attention that we draw the secant line between x1 and the previous point, which is x0. So between this point and this point, and we draw the new secant line, which is this line. Okay. So the new point, the intersection of this secant line with the x-axis, is x2. So this is our new point. And again, we seek the value of fx at this point, x2, which is fx2. And again, we draw the new secant line between x2 and the previous value, which is x1. So x1 and x2, the new secant line is this line. And the intersection of this new secant line with the x-axis is x3, which is this point. And this is our new point. And again, we seek the value of fx at x3, which is this point, and we draw the new secant line between x3 and the previous x, which is x2, so this point. And this is our new secant line. And as you can see, the new intersection with x-axis is x4, which is this point. And as you see, we continue this process and we are approaching to the root of fx, which is around here. So yeah, that's the secant method. The difference with the secant method and false position method will be illustrated later. But pretty much this is the fundamental of the secant method. The equation that we use for the secant method is shown here. It is based on interpolation of 2 points for the line, pretty much similar to what we obtained for the false position method. Here I stands for iteration, and I should be equal to 1 or greater than 1, and we assume that fxi is not equal to fxi minus 1, which is from the previous iteration. Also remember that for this method, we call a as x minus 1 and b as x0 for the interval of a and b. This is very important to pay attention, and these are the starting point of our iteration process, and then we obtain x1, x2, 3, and so on. Okay, let's compare the secant method with the false position method through this illustration. On the left, I'm gonna show you the secant method through illustration. Let's assume we are looking at the root between point 1 and point 2 in the interval. So we draw the secant line between point 1 and point 2, which is this line. And then the intersection of this line with the x-axis is point 3. And we seek the value of fx at point 3. So now we have this new point, and we compare this new point with the previous one. I emphasize with the previous one. The previous point is point 2. So we draw the new secant line between point 2 and point 3, which is this one. And the intersection of this line with the x-axis is a new point, which is point 4. So this is the new point. And we continue this process, and we approach to the root. So the important thing about the secant method is drawing the secant line between new one and the previous point. So that's very important. But on the right, we have the false position method. Again, for the same curve and for the same interval between point 1 and point 2, we draw the secant line, which is this one again. And remember that for the false position method, always one end point is fixed and active. For this case, point 1 is fixed due to the convexity of the curve. So the intersection of this secant line with the x-axis and the value of fx at that point is 0.3. So now we draw the new secant line between, again, the fixed point 1 and the new point 3. So the new secant line is this line. And that gives us the new point 4 here, and as we see, if we proceed, we approach to the root based on the false position method. So for the false position method, we always have interpolation between the two lines, but for the secant method, we also have extrapolations. For example, the secant line between point 2 and 3 and the intersection of that line with the x-axis is the extrapolation. So this one is extrapolation. That's the difference between the secant line and false position method. Also, false position converges less rapidly than the secant method, but it is more certain. So we know that we approach to the root. But for secant line, for some circumstances, you may not converge to the root, which is not the scope of this video. Okay, let's take a look at the example that we used for the bisection method and false position method. We have this function fx equals x over 2 squared minus sine x in the interval 1.5 and 2. And as you can see, the value of fx at 1.5 is given here, and also at 0.2 is given here, and we consider 1.5 as x subscript minus 1 and 0.2 as x0. So in the table below, we enter I, the iteration minus 1, and also xi 1.5, and the value of fx I at point 1.5, and also at iteration 0 at 0.2, the upper interval, and the value of fx at 0.2. Okay, we also use this formula, this equation, as we explained before, to obtain the new value of x for iteration I plus 1. As you notice, we need the value of xi at iteration I, and also the corresponding value of f at xi, and also the iteration at xi minus 1. So the value of xi at iteration I minus 1, and also fx at iteration I minus 1. So basically we need 4 values. That's why in this table we have these 4 values. So we use these 4 values to obtain the value of x at iteration 1. Okay. To obtain the value of x at iteration 1, I use Desmos graphing calculator here, which is very helpful, and I'm going to show you how to use this calculator to obtain the values of x. Okay, let's put the fx into the calculator. Here I define the value of fx. So x divided by 2 squared minus sine x. So this is the graph of the function, as we already saw. We want to have the values of fx at different points, so we are interested on the value of this function at different x values, so we use this table here. We have point 1.5 and 0.2. We already have these values, as we can see. So this table helps us to obtain the value of fx at corresponding x values. But we want to see and obtain the new x using this equation. So we put this equation in the Desmos graphing calculator, but please pay attention that we have 4 variables here: xi, fxi, xi minus 1, and fxi minus 1. So we have 4 different values here. So we have 4 variables, and therefore I'm gonna call xi, for example, for iteration 1, this value is xi. Let's call xi n. This value for iteration 1 is xi minus 1. call it, for example, M, because in the Desmos calculator we don't have xi minus 1, so we have to select some other variable names. That's what I'm doing here. For fxi, let's call it q, and for fxi minus 1, let's call it p. Okay, now our new equation can be rewritten as xi, which is n, minus fxi, which is q, times xi n minus xi minus 1 m divided by fxi q minus p. So this gives us the new value of xi plus 1. So I'm going to use this equation, which is similar to the left one, in the Desmos calculator. So here I define the new equation. So n minus q times n minus m divided by q minus p, q minus p, and we hit the all here. Okay, for n, which is our xi, we give the value of 2. For q, which is our fxi, we put the value of 0.0900703. For m, which is our xi minus 1, we put 1.5. And for p, which is our fxi minus 1, we put minus 0.4349995. Okay, this is our new value here, 1.913733. So I'm gonna put that value in the table. So we have the new x value is 1.913733. Okay, and the value of f(x) at this point is, let's put that value here, 1.913733. So that value is this one, minus 0.026177776. So I'm going to put that value here in the table. So minus 0.0261, let's round it up, 8. So this is our new value for fxi. So that's for iteration 1. For iteration 2, we follow the same procedure, but at this time our new xi and xi minus 1 are 2 and 1.91373. You know, the values are updated, so we just update these values. So this is new m, this is new n, this is new q, this is new p. So again, we use the same equation. Our new n is 1.9133733. New m is 2. New q is minus 0.026178, and new p is our old q, which is 0.090703. So this gives us our new x, which is 1.93305.4. So, and if we put that value here in the table to get the new fxi, it's 1.93305.4. So it gives us minus 0.000924. Okay, so we put these values in the table. Let's do that. For iteration 2, our new x is 1.93305.4, and our new fxi is minus 0.00924. So we can see that our fx is getting smaller, it's approaching to 0. And if we continue for the third iteration, I'm not gonna use the calculator, I'm just gonna give you the values. For the third iteration, we get 1.93376 and the new fx is 0.000010, and for the fourth iteration we get 1.9337753, and our fx is minus this value. So as we see, we are obtaining fx as 0, which is the purpose here. If you remember the example, we want to obtain the root of the fx, so where we have the value of 0 for fx. So we are approaching the root, and the root is this value. With 4 decimal digits, we can say our x is, for the root, is 1.9338. So using the secant method, we obtain the root of this function through iterations, and as you see, this Desmos calculator is very helpful here, and I think that example is useful to understand the steps and procedures to obtain the root of a function using the secant method. If you have any questions, leave a comment down below and I will get back to you as soon as I can. If this video helped you in any way, please hit the like button and subscribe if you enjoy our content and would like to see more. Thanks for watching.